My dear students, Assalamu alaikum and adab. Today in this lecture, we'll discuss the development of shear stresses in the beams and their evaluation. So first of all, we begin with these shear stresses. What basically this shear stress is, how it gets developed in a beam. So from the basics, we see that if we have a beam which is loaded, say it is loaded with UDL of intensity W per meter, the effect of this load on the beam will be that it will lead to the development of shear force, which will vary along the cross section, along the longitudinal section of the beam, and the development of bending moment as well in this particular beam. Say if we see the variation, the shear force will vary something like this. It will be maximum at the support and it will go to 0 at the center. Here it will be WL by 2 and WL by 2 here also. This is the variation of shear force in the along the length of the beam. Then it will also lead to the development of bending moment with maximum bending moment at center, which will be equal to WL square by 8. This is the bending moment type. The effect of this shear and bending moment is that this bending will lead to the development of bending stresses. It will lead to the bending of the beam, something like this, which will produce bending stresses in the beam. Similarly, this shear will also lead to a sort of failure in the beam, which we call shear failure, in which no bending takes place. Shear failure is explained in this particular diagram. At the critical section where shear is excessive, the beam may break down into two parts like this. This part may go upwards, this may come downwards, and this becomes the failure plane. This is the failure plane because of the excessive shear at the critical section, and the failure takes place like this. So, if that shear force which leads to such type of failure, if that shear force we divide by the cross-sectional area, which is the resisting area of this shear, we'll get a stress called shear stress. So this shear stress will act on this particular cross section, and if excessive, then it may lead to such type of failure in a beam. So this type of stress, which is on the transverse, acting on the transverse section of the beam, this is resisting the shear force, is known as shear stress. If we take out one element, say a small element out of this, and see where these shear stresses are acting on this element, say this is the element. In this element, we have shear stress acting like this. This is the longitudinal axis, this is the transverse axis. So this is acting along the transverse axis. So this is the position, this is the shear which is acting. It's forming a sort of a couple here in the anti-clockwise direction. So in considering the equilibrium conditions, another couple should develop, another moment should develop in a clockwise direction to balance the anti-clockwise moment developed. So these stresses are known as shear stresses, which are acting along the transverse axis of the particular member. In order to counterbalance those, another set of shear stresses is acting, but this time this is along the longitudinal axis of the beam. So these are known as longitudinal stresses. Longitudinal stresses. These longitudinal stresses get developed on their own, and they are also known as complementary stresses. So shear stress acts along the cross section of the beam, along the transverse section of the beam, and this is developed because of the effect of shear force, which is developed because of the load acting on the beam. Now we need to evaluate how these shear stresses can be evaluated and how they vary for various cross sections from top to bottom. Say this is a beam which is having a length of L, width B, depth of the cross section is D, and it is being loaded by certain load acting on it. Let's take two cross sections for our analysis. This is one. Say this is section AB. This is section CD, and the distance between them we take as dx. If I draw this element separately over here, so it will look like this: section AB, section CD, and their length is dx. This is the cross section. Okay, say this is section AB, this is section CD. The distance between them is dx. This is width B and the depth of the section D. This is the neutral axis. Okay, then for our analysis we'll take a small element. Say for our analysis we'll take a strip above the neutral axis. Say this is EF, and the distance of this is y from the neutral axis. Okay. Now we will evaluate at these sections AB and CD and see the unbalanced force, and then somehow derive the equation for shear stress. Now if I can consider bending stresses which are developed due to the load acting over the member. If we have bending stress at section AB, let that bending stress be equal to sigma. Okay, we have bending stress at section CD, which will be slightly more than this. Let's say, I don't know actually what it is, so let's take it sigma plus d times sigma, slightly more than sigma. Okay, then from the bending equation we have m upon I is equal to the sigma upon y, or this bending stress shall be equal to m upon I multiplied by y. Okay, this will be our bending stress in terms of mi and y. Now if I replace it here, we have bending stress at AB shall be equal to m upon I multiplied by y. Okay, we replace the sigma here also. It will be m upon I multiplied by y, and here also d times m upon I into y. Okay, this will be our bending stresses at the two sections under consideration, AB and CD. Okay, these are stresses. If we convert it into force, we'll have force at AB. That will be equal to force is stress multiplied by area. We have stress as m upon I into y, and let the area of this strip be equal to d times A. We are considering this strip. This will be the plane where shear is acting. So we'll have this plane where the shear is acting. Let's consider the area of the strip as dA, and force at CD shall be equal to m upon I into y. This is again force plus d times m upon I into y multiplied by dA. We multiplied it by area of the strip, which is under analysis, and we have calculated the forces now acting over the section AB as well as CD. Now we know that shear force is basically what? Shear force is the unbalanced force. So we need to calculate unbalanced force. So unbalanced force. Okay, unbalanced force means the difference of the two. Unbalanced force over the strip under consideration will be equal to force at AB and CD, the difference of the two, or force at CD minus the force at AB. Okay, we'll have to subtract these. So when we subtract this, we will have m upon I into y plus d times m upon I into y multiplied by area dA minus this force m upon I into y into dA. Okay, this will now be the unbalanced force. So this unbalanced force, this m upon I will get cancelled over here. It will be left out with d m upon I into y into dA. This will be the unbalanced force. Okay. if this is the unbalanced force for the strip, we need to calculate the total unbalanced force. Total unbalanced force means, now this is the failure plane, this is the plane of failure, that is this area, the plane will be the failure plane and the section will get separated at this particular level. So the upper area, the area which is above this, will be separated out from the rest of the area, from the rest of the cross section. So this is the area for the entire section above the section or the plane under consideration, which will get separated out. So I need to extend this unbalanced force for the entire area now. So the area of this strip, let's take it equal to A now. A is the area of that portion which is above the level where we were considering EF, above that level, and now this Y will go to the CG of this particular area A from the neutral axis. So this area A is having a distance of its CG from the neutral axis as Y bar. So when we find out the total unbalanced force, we need to integrate this. Integrate it M upon I into Y into dA for the area above the plane under consideration, and then accordingly we see the distance of its CG from neutral axis also. So this D, when we integrate this dA into Y, this area will be replaced by the area of the strip above that is A, this Y will be replaced by Y bar, and the total unbalanced force will be equal to dm by I A into Y bar. This will be the total unbalanced force over the strip which is above the plane of shearing, where the plane shearing stress has exceeded and the member has separated out from that particular plane. Now this is still force, this is now unbalanced force, which is the total one after integrating the things. Now we have to find out stress developed. So stress is always force per unit area. So if I need to convert it into stress, I need to divide it by area. So we have shear stress. If I say shear stress, we represent it by Q. This shear stress shall be equal to this force, unbalanced force, dm upon I into Y, A into Y bar. This is to be divided by the area of this strip where the failure has taken place, because we have to find out per unit area. This shaded area is which is resisting the stress, and the area is equal to this length dx and this width b. So dx into b was the area of the plane where this shear stress was acting. So this will ultimately be evaluated as, say this becomes dm a Y bar divided by dx multiplied by b. Okay, this I will also come down. Now dx by dm by dx, this is the moment, bending moment, divided by for some distance. It will be termed as force. It will be converted into force. Dm by dx will be nothing but force. So we will have shear stress as shear force F, area A, Y bar, CG distance from neutral axis of the area A, divided by I, moment of inertia, and B is the width at the section. So this is the equation for shear stress. This is shear stress, which is equal to shear force multiplied by area. Area of which area? Area above the level where we are considering the shear stress. Area of the cross section above that particular level of plane of failure. Distance Y bar is the distance of that area A, CG of that area from the neutral axis. I is the moment of inertia. B is the width of the section where we are calculating shear stress. This may vary if the cross section is not having the uniform width, then B may vary along at different levels. So this is our general equation for shear stress, and we need to analyze any beam for a particular cross section using this equation. Now we will extend this equation and see how we evaluate these shear stresses in various cross sections. Say first of all, if I take a rectangular cross section, this is a rectangular beam now of width B, depth is D, this is the neutral axis. Okay. This is being acted upon by certain load which will ultimately give us shear force in that particular member. Now, we need to see the variation of shear across its cross section. That means at various levels, what is the shear stress developed and how it varies. So, we need to draw a shear stress diagram. For this particular beam of this cross section, we know this is the neutral axis, and the equation for shear stress Q is now F area Y bar divided by I into B. Okay. For this particular section, we will have moment of inertia I as B into D cube divided by 12. Okay. Area we'll have to see. B is the width. Width is constant throughout, so B will always be B. A and Y bar we'll have to see. Now area. If I take shear stress at this level, this and this are same. If I take the element at the outermost level, that means I take this level at D by 2 from the neutral axis. This area will be 0 because there is no area beyond this. So when A is 0, Q will be 0. So it's always 0 here and 0 here. So shear stress will be 0 at both the extreme edges of the cross section. Now I need to calculate it here, say here. When I am on the neutral axis, this area will be equal to this shaded area. Okay. When I am on neutral axis, area shall be equal to B is the constant width into D by 2. This area. Okay. Y bar is the distance of CG, center of this area, CG of this area from the neutral axis. So this is already D by 2. This will be D by 4 now. Okay, this is Y bar. So Y bar shall be equal to D by 4. Okay. So this is our area under consideration, Y bar under consideration. Width of the section is constant throughout. This is our general equation, and I am here. I am on neutral axis. If we put these values here, F is shear force as it is. Area B into D by 2, B into D divided by 2. Y bar multiplied by D by 4 divided by I is B D cube by 12. So B D cube divided by 12, and B is as it is. This will be our modified values now. If we further simplify this, we will have shear stress equal to F shear force BD square, B into D square, 4 into 2 is 8. Inverse of this 12 upon B square D cube, B square D cube. Okay. This is the simplified form. We can further simplify it. We'll have 4 into 2, 4 into 3. So 3 by 2. This B will go with this square. This D square will go with this cube. We'll have B and D there now. So this shear stress is now equal to 3 upon 2. Here it is F divided by B into D. This is what is left out now. This F upon BD is nothing but shear stress, average value of the shear stress. So the shear stress at the neutral axis, where A is going to be maximum, we can call it Q max also, shall be equal to 1.5 times the average shear stress. So at the center, at the neutral axis, at the CG, the shear stress is going to be maximum for this particular rectangular section, and that shall be equal to 1.5 times the average shear stress in the member. Say for example, it's somewhere here. This is Q max. Here it was 0 at both the ends and the variation is parabolic. The shear stress diagram is going to look like this. This is the shear stress diagram. For a rectangular section subjected to certain load which leads to the development of shear force F. So this is our shear stress variation, and the maximum this shear stress is going to be 1.5 times the average shear stress. Okay, this was for a rectangular section. Now let's analyze another section, say a circular section, where we'll also find this, what this Q max is equal to. Say our cross section is now circular section of certain diameter d. This is the neutral axis. These are the upper edges and the lower one. The diameter of this particular section is d. Okay, this is the circular section now. For this circular section, if I need to draw the variation of shear stress, I need the shear stress diagram. How shear stress is going to vary for this particular cross section. If I calculate shear stress at this point, our shear stress equation, basic equation is F area y bar divided by I into P. Here above this there is no area, A is 0, so shear stress is 0, so we will have 0 value here. 0 value here. Now we will have to see what value for the neutral axis. When our location is at neutral axis, what shear stress will be getting? So we are at neutral axis here. The area under consideration will be this shaded area. This will be the area under consideration now. This, our failure plane is here. Above this, half of the area of this circle is applicable. So area A. Area is this shaded area. We have equal to pi by 8 d square. Area of the semicircle. CG will be somewhere here. So y bar will be this location. Y bar, here y bar is equal to 4r by 3 pi. This CG is located at 4r by 3 pi. In terms of d, if I calculate, so 2 times r will be d, so it will be 2 into d by 3 pi. So we can take it like this. Okay. So this y bar we can take 2d by 3 pi. Inertia, moment of inertia for the circular section will be pi d to the power 4 upon 64. B is equal to d, diameter of the section, it is a circular one. If we put these values here, what we will have is Q equal to shear stress will be equal to F is the shear force. Area under consideration is pi upon 4, pi upon 8 d square. It is for the semicircle only. Pi upon 8 d square is this A. Y bar will be multiplied by 2d by 3 pi. Okay. This entire term divided by I is pi d to the power 4 by 64. B is equal to d. Okay, this is what we will get after substituting these values. Now let us simplify to find out the maximum shear stress for a circular section. So here, if I cut this to 1s to 4s, this pi will also go. We will be left out with Q max shall be equal to shear force F. We will have 4 into 3 is 12 d cube divided by 12. This will take inverse multiplied by 64 pi d to the power 5 d to the power 5 now. Okay. If I simplify it further, 4 into 3, 4 into 16 will be left out with f. This d cube will go, it will become d square here. This will be 16 divided by 3 pi d square. Okay. Or if I convert it in terms of area, I will have 4 here, this will be 3 here, pi by 4d square here. This pi by 4d square will be equal to area. Pi by 4d square is equal to area, and ultimately our shear stress Q max shall be equal to 4 upon 3 times F upon area. F is here, this is F divided by area, pi by 4d square. Shear force divided by the area is shear stress. So 4 by 3 is a constant. This will be shear stress, average shear stress, tau AB. This was shear force, this was divided by area. So we have shear stress here, 4 by 3 is a constant over here. So in a circular section, we have the average 4 by 3 times average shear stress shall be the maximum shear stress which is acting at the neutral axis. So this value will lie over here, that is 4 upon 3 times average shear stress, and the variation will be parabolic. This is the case for a circular cross section where we will have maximum shear stress or the shear stress at the neutral axis equal to 4 by 3 times the average shear stress. Okay. Then we have other cross sections, say we have I sections or some other sections where we need to find out the shear stress variation. Say I take the example of I section, which is a symmetrical one. This is the I section. Symmetrical I section with bottom and top flanges of the same size. Okay. If this is the neutral axis and we need to draw the shear stress distribution for this particular cross section, we need to draw it at various levels. These are the levels. If we need to draw shear stress diagram, for this particular section, we need to find out shear stress at various points. Say this is 1, 2, 3, 4. Then it is symmetrical. Once again, it will be 3, 2, and 1. Okay. So what we do, our basic equation remains the same. Shear stress shall be equal to shear force, area about the section, CG from neutral axis, AY bar divided by I into B. Now B is not constant throughout, so that has to be taken care of. B is changing. Here it is flange width BF. Here it is width of the web BW. So B will change. Sometimes it will be BW, other times it will be BF, like that. So we need to calculate shear stress at particular location along the length and draw its variation across the cross section. So if I take point 1, first of all, area above this is 0, so this value will always be 0. So here and here the values are 0. Now come to 2. If I am at section 2, area under consideration will be the area of rectangle 1. This is rectangle 1. This is similar to this. This is rectangle 2. Okay. Inertia we need to calculate. Inertia will be the inertia of rectangle 1. 2 times you can do it, plus the inertia of rectangle 2. Or it will be B into D cube divided by 12 plus A1 H1 square. This is for rectangle 1, where H1 will be this distance, CG of this rectangle from the neutral axis, and we'll multiply it by 2 because this is another flange of the same dimensions. We'll add B into D cube divided by 12 for a rectangle 2, and no parallel axis theorem here because it is CG is coinciding. So we'll find out inertia here. Width we will see it will be different for different sections. For section 2, area applicable is the area of rectangle 1. y bar will be half of this depth, inertia is this, and b for this particular section, this b at section 2 will be equal to bf. But at the same level, we have 0.3 also, where b will be equal to bw. So we calculate it twice. At section 2, we take at section 2 b as bf, area as area of the rectangle, y bar as distance of this CG from the neutral axis. Okay, this will be y bar initially, and inertia from this equation. So we find out some value and put it here. This is the value at section 2, the variation is parabolic, and same value will be here repeated because of the symmetry. Okay, but at the same plane you have another section 3 where area is same, y bar is same, but b is different. I is same, b is different. Now b at section 3 shall be equal to bw. Because the width is just changing when we are shifting from 2 to 3, b gets changed from bf to bw. So you will take bw in this instance now, and at the same level you will get an increased value of shear stress, which we will show by this line, a horizontal line, which will be the shear stress at 3 now. This is shear stress at section 2, this is shear stress at section 3, 2 and section 3. Okay, then we come to the neutral axis, that is at point 4, shear stress at 4. There the area now will increase. The area will be equal to the area of rectangle 1 plus this area, this portion of rectangle 2 also. So 1 multiplied by its corresponding y bar, 2 will find out the CG, and this will be y bar applicable for area 2 now. Okay, so we will have a1 into y1, a1 into y1 plus a2, this area, into y2 or y bar for its applicable y bar. So this y for section 4, we will distribute this a into y as, say this is a1 y1 bar, a2 y2 bar, and we will add these together. Then we will find out a summation of a into y bar. Shear force is okay. I will remain same. B at section 4 shall be equal to bw. Okay, and the value you will obtain here will be much more than this Q3. So this will be Q maximum or Q4. Okay, this will be the maximum value of shear stress at the neutral axis, and we join it like this. This will be the shear stress diagram with maximum value at shear stress, two values at this particular plane, because you will be having 0.2 as well as 0.3 as the change because of the change in the width. So there will be the variation will appear to be a horizontal line over here, maximum value at shear at the neutral axis, and the diagram will be something like this. Now there may be one more case where the section is not symmetrical. The section is not symmetrical. Say I have a T section which is not symmetrical now. Certain changes in the shear stress diagram will occur. Now here we'll have to find out the CG first. We don't know that, we know that it is not at the center, it will be somewhere towards the top flange. So we'll find out the CG first, and then we will go for the shear stress diagram, which will be drawn here, will be shown here. Now for this particular section, we will have two widths. This is the width of the flange BF, which is for rectangle 1. For rectangle 2, we will have width as BW. We'll find out shear stress at point 1, at point 2. This will be point 3 at the same plane, point 4. This is same 0 here also. As 1, it will be also 0 here. Our equation is F area y bar divided by I into B. For I, we need to find out the CG first. Y will find out from the bottom or from the top. We'll find out the CG location first of all by the equation. y, if you take it y, this y will be y dash, so y dash will be equal to a1 y1 plus a2 y2 divided by a1 plus a2, where a1 and a2 are the areas of the rectangles and the y1 y2 are the distance of the CG of these rectangles from the base. Okay, now shear stress is 0 here, we know, here it is also 0. Come to point 2. At 2, this is the area which is applicable. So area is equal to this BF multiplied with the thickness of this flange, depth of the flange, DF, depth of the flange. This is the area and center is this. So y bar will be from the neutral axis. Okay, so DF into BF is the area, y bar is this distance, inertia, we'll find out the inertia of rectangle 1 and summation of rectangle 1 and rectangle 2, where parallel axis theorem will have to be used. And we find out some value of shear stress, which will be Q2. Width applicable at 2 is the width of the flange. Okay. At the same plane, that is Q3 now, Q3, all the values will remain same, only this B will change from BF to BW. You will get some increased value here. This will be Q at 3. Okay, then come to neutral axis. When we go to the neutral axis, some area is increased now. We have to take this area also. So this term A into Y bar, we shall take equal to A1 into Y bar, say Y1 bar, I will name it as Y1 bar, plus A2 will be area, this area now, this shaded area, into Y2 bar. Y2 will be the center CG from neutral axis. This will be Y2 bar. Summation of this will become A into Y bar. F is same, I will remain same, B will be BW. So you will have an increased value. That will be the maximum value at the neutral axis somewhere here. This is Q max or Q at 4, and this will join here and then go to 0 over here. This will be our shear stress diagram. Okay guys, this is how we draw the variation of shear for a particular cross section and for a beam with certain load which will give us shear force. So if we sum up, we see that the effect of the load is to create bending stresses as well as shear stresses in the beam. Shear stress will depend upon the shear force and the section where we are calculating it. What is the shear force there? Shear stress will be calculated accordingly. Our shear stress equation is Q equal to F A Y bar upon I into B. I we are familiar with. This will be the inertia, moment of inertia of the cross section. F will be the shear stress at the section where we are calculating the shear force. This A will be the area above the level where we are calculating shear force. A will be above that particular level. Say, if I show it once again here, if this is the rectangular section, this is my neutral axis, I am calculating shear stresses at this particular level. A will be area which gets sheared out, that is above that particular level. It will be the area A, and its distance from the neutral axis will be this Y bar, and B will be the width of that particular section where we are calculating the shear stresses. So from this particular equation we can calculate, we have seen that we can calculate these shear stresses at various levels from top to neutral axis to the bottom of the section. If the section is symmetrical, then the values will get repeated. If the section is unsymmetrical, we need to find out its CG first, then we need to calculate the values which may not be same, which may not be symmetrical from the above and below the neutral axis, which we need to calculate sequentially, and care needs to be taken about this B. This B will depend upon the section where we are calculating the shear stress. It may not be same, it may be same in a circular or a rectangular section, but if it is an I section, T section, L section, channel section, B needs to be seen whether we have to take the flange width or the width of the web. So accordingly we can draw the variation of this shear stress in form of a shear stress diagram. Thank you.